Hi friends, welcome to our YouTube channel Naraj Academy. The main aim of this lecture is to discuss about the electromagnetic theory, previous year questions of the ESE examinations in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button so whenever we upload a new video, the direct notifications comes from mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So now we are going to solve the 21st question. See the question here. Which one of the following statements does not state that the electrostatic field is conservative? So out of these four options, which statement is not going to tell you that this is the electrostatic field is a conservative field? So out of these four options, option B is the correct solution of this question. So let's solve this numerical. So because of static charges, the electric field which we are going to produce is called as the electrostatic electric field. So if this electric field is going to have a nature which is a conservative nature, means the work, or we can say the work done in the electrostatic field is independent of the path travel, and it is only depending upon the initial position and the final position. Means suppose is the initial position, the final position, see no matter whatever the path, suppose this is the path 1 and this is the path 2, see the work done in the path 1 and the path 2 is same. If it is a E bar is a conservative field, means it is going to independent of the path, but only thing it is going to concern is the initial position and the final position. If the two different paths have the same initial position, the final position, the amount of work done in order to carry a charge from initial position to final position in that conservative field will be always same. That is the meaning of the conservative field. So now here let me tell you two important formulas of the potential difference and also the amount of work done if you want to bring any charge from point A to point B in a source of charge Q, which is VAB is equal to VB minus VA is equal to minus integration of A to B E bar dot DL bar. This is a voltage difference formula, and the amount of work done is equal to minus Q into integral A to B E bar dot DL bar. So if you see carefully, W is a function of integral of E bar dot DL bar, and V is also the potential difference, which is also a function of integral of A to B E bar dot DL bar. So we can say, suppose if you are going to make a closed loop, means I am going to make a initial position is equal to final position. Suppose if I am going to make a closed loop, means initial position is equal to final position, means we can say here VB is equal to VA, because we are going to make a closed loop, so therefore this value will become 0. So therefore this integral, the closed line integral, because we are going to make a closed line integral, so therefore this value will become 0. So therefore the closed line integral of E bar dot DL bar is equal to 0, because we are going to make a closed path, means the initial position is equal to final position. So therefore we can say only in a closed loop we can say the net potential drop is equal to 0, and W is also a function of E bar and DL bar integral, as the overall integral value will become 0. So therefore we can say W is also equal to 0 in a closed loop. So therefore we can say here in a closed loop always the potential difference is equal to 0, and also the amount of work done in closed loop in a conservative field is always equal to 0. But if it is not a closed loop, suppose if it is not a closed loop, means we can say work is not equal to 0 and the potential difference is also not equal to 0. But only if it is a closed loop, then only we can say if you are going to make a closed loop in a conservative field, the net potential difference is equal to 0 and the amount of work done is also equal to 0. But here, so now here with the help of Stokes theorem, so Stokes theorem is going to relate a closed line with a open surface. So therefore closed line integral of E bar dot DL bar is equal to open surface integral of curl of E bar dot DS bar. See, as the LHS value is equal to 0, so therefore we can say del cross E bar is also equal to 0. So therefore we can say curl of electric field is equal to 0, means there is no curl position, or we can say there is nothing curling if it is not at all present in the electric field. Only the electric field is going to purely diverging, it is going to either diverge, but it is not going to have any curl mechanism, or we can say E bar is the irrotational field. So therefore we can say the curl of electric field is equal to 0. Suppose here I can write this as a delta V is equal to minus E bar dot delta L. So E bar dot delta is nothing but So you can take, see, A bar dot B bar is equal to mod of A into mod of B cos theta. So I'm going to expand in that manner, which is E into delta L into cos theta. So I can take here, I can write in this fashion, which is E cos theta is equal to minus del V by del L. So here theta is the angle between the E bar and the del bar. So here, suppose if theta is equal to 180, what is going to happen? Suppose if theta is equal to 180, cos 180 is nothing but minus 1. So minus minus cancels, we are going to get the maximum amount of electric field we are going to get, which is delta V by delta L. So here, the maximum amount of electric field we are going to get only if we are going to move with opposition. Suppose if this is the electric field, then we have to move in the opposite to the, so you have to move the charge in an opposite manner to the electric field, then only we can say the electric field will be maximum. The maximum electric field will be delta V by delta L. Whenever we can say, if you are going in the opposite direction with respect to the electric field, then only we can say the gradient is very, very higher. So therefore we can say here, finally E bar is nothing but minus del V. So here electric field is a negative of the gradient of the scalar electric potential, means always the gradient is always perpendicular to a scalar function. So therefore we can say whenever anything is a perpendicular, means there is no curling effect. So definitely we can say this is also going to tell you that here there is no curling mechanism, only it is a radiating one. So therefore we can say here the curl of electric field is also equal to 0. So E bar is equal to minus del V. So only in a closed loop, only the net potential is equal to 0 and net work done is equal to 0. Otherwise these both are not equal to 0. So we can say whenever electric field is a conservative, means we can say even the closed line integral of E bar dot dl bar is equal to 0, and also we can say the curl of electric field is equal to 0, and also here the electric field is equal to negative of the divergence, negative of the electric scalar potential, and only in a closed loop the net potential drop is equal to 0, otherwise it is not equal to 0. So now we are going to solve the 22nd question. See the question here. Sphere of radius A with a uniform charge density rho v coulomb per meter cube, then shall have electric flux density at r is equal to A equal to. So here they are given a sphere, solid sphere of radius A. So therefore we can say here, now of a uniform volume charge density rho v coulomb per meter cube, then what is the electric flux density at r is equal to A? Means radius at r is equal to A, we need to find what is the electric flux density. So out of these four options, option A is the correct solution of this question. So let's solve this numerical. So now here let me assume a solid sphere of radius A. Suppose I am going to assume a Gaussian sphere of radius r. Let me assume this radius is greater than A. Then I want to know what is the expression of the electric flux density, and then finally I can keep r is equal to A in order to get the value of the electric flux density. When at r is equal to A, I can easily figure out. So now I want to know what is the general expression whenever the radius of this Gaussian surface is higher than the radius of this sphere, then what is the electric flux density we need to figure out. So here in this question they also given the volume charge density. The volume charge density is nothing but charge enclosed by volume. So therefore here, see, by using this Gauss law, so by using the Gauss law we can figure out the total amount of flux which is passing through this closed surface is equal to the amount of charge enclosed, which is, so total flux through this closed surface is equal to surface integral of d bar dot ds bar is equal to charge enclosed. So now here rho v is equal to charge enclosed by volume. See, the charge is going to present only within the volume of this sphere. So therefore we can say charge enclosed by this sphere is nothing but it is a charge of the body. So therefore charge enclosed by volume of the body, which is 4 by 3 pi a cube. So A is the radius of the sphere, so therefore we can say volume of a sphere is 4 by 3 pi a cube. So therefore if you do this one cross multiplication, so with the cross multiplication we are going to get charge enclosed is equal to rho v into 4 by 3 pi a cube. So now here ds bar, so ds bar, what is the surface area? See, let me take a small amount of surface area. What is the surface area? A small amount of area in a spherical coordinate system. See, we know the value of the ds bar. It is the normal vector will be in the direction of the air cap. So if you want to know what is the ds in the air cap, then we have to go for the product of the a phi component and also a theta component. See, a phi component is r sin theta d phi and a theta component is r d theta. If you multiply these two things, we are going to get the area in the direction of the air cap, which is r square sin theta d theta d phi air cap. And also here let me assume d bar is always radiating outside. So therefore d d bar is equal to d into air cap. So this is what I have written here. So therefore now I can substitute all these things here, and if I do the dot product of these two things, I am gonna get d into r square sin theta d theta d phi is equal to charge enclosed. I can write rho v into 4 by 3 pi a cube. So now here I want to cover this whole Gaussian surface. If I want to cover whole Gaussian surface, I have two variables theta and phi. So theta will vary from 0 to pi and phi will vary from 0 to 2 pi. So therefore we can say theta is going to vary from 0 to pi and phi is going to vary from 0 to 2 pi. R square sin theta d phi is equal to same thing. So basically if you do this integration, if you do this double integration of this value, or either we can say directly this is a surface area. So surface area of a Gaussian sphere is nothing but of any sphere, the surface area is 4 pi r square. So therefore we can write simply or directly 4 pi r square. So d into 4 pi r square is equal to rho v 4 by 3 pi a cube. So if you do the simplification, we are going to get electric flux density is equal to rho v into a cube by 3 r square. So therefore in vector representation d bar is equal to d into air cap. So therefore this is the electric flux density at any point which is outside the sphere, which is rho v a cube by 3 r square air cap, and its unit is coulomb per meter square. But in this question they are asking only at r is equal to a what is the electric flux density. So in the place of r you can substitute a. So therefore if you do the simplification, if you substitute in place of r, if you substitute a, and if you do the simplification, we are going to get rho v a by 3 ar cap. So therefore this is the correct solution of this question, or we can say the electric flux density at the surface of the sphere, which is rho v a by 3 ar cap, and its unit is coulomb per meter square. The unit of the electric flux density is nothing but coulomb per meter square. See, basically electric flux density, it is called as the flux per area. So flux per area, the unit of the flux is coulomb and the unit of the area is meter square. So therefore we can say the unit of the electric flux density is coulomb per meter square. So this is the correct solution of this question. So now we are going to solve the 23rd question. See the question here. 6 capacitors of different capacitance C1, C2, C3, C4 and C5 and C6 are connected in series manner, and also they are given C1 is greater than, C2 is greater than, C3 is greater than, C4 greater than, C5 greater than, C6. Then what is the total capacitance? Almost equal to. Then what is the net equivalent capacitance? It is nearly equal to which one? So out of these four options, option D is the correct solution of this question, which is capacitor 6. So let's solve this numerical. So in this question they are given 6 capacitors, they are going to connect in series manner. So as they are connected in series manner, the charge will be same for each and every capacitor. But only thing is the supply voltage is going to get drop across the each individual capacitor, which is V1, V2, V3, V4, V5, V6. So we can say net equivalent voltage is equal to sum of the individual voltages, as charge is equal to Q is equal to C into V. So therefore we can write V is equal to Q by C. So therefore now V can be write Q by C. So charge is same for each and every one. So therefore we can write Q by C equivalent is equal to Q by C1 plus Q by C2 plus Q by C3 plus Q by C4 plus Q by C5 plus Q by C6. So Q all are going to get cancels. So finally we are going to get 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4 plus 1 by C5 plus 1 by C6. In the question they already given that C1 is greater than, C2 is greater than, C3 greater than, C4 greater than, C5 greater than, C6. So whenever this is the true, then we can say the reciprocal will be in the reverse manner. So therefore 1 by C1 is less than, 1 by C2 is less than, 1 by C3 less than, 1 by C4 less than, 1 by C5 less than, 1 by C6. So we can say this 1 by C1, 1 by C2, 1 by C3, 1 by C4 and 1 by C5 all are less values when compared to 1 by C6. So therefore now we can neglect all these values. So therefore we can say 1 by C equivalent is nearly equal to 1 by C6. So 1 by C equivalent is nearly equal to 1 by C6, and if you take the inverse, we are going to get the equivalent capacitance is nearly equal to C6. Or even we can say that whenever they are going to have this type of, always the C equivalent will be lesser than the minimum value. It is lesser than the minimum value. Out of all the capacitors, the minimum value is C6. So therefore we can say the C equivalent is less than the C6, or we can even say the C equivalent is nearly equal to C6 value. So therefore the C equivalent is nearly equal to C6, but not exactly, it is nearly equal. So therefore we can say option D is the correct solution of this question. So now we are going to solve the 24th question. See the question here. Consider the following statements for an electrostatic field. So out of these three statements. We have to choose which one is the correct statement. So the statement one is its curl is 0, and second one is it is negative gradient of the scalar potential V phi, and it is a conservative. So out of this, which of the statements are correct? So out of these four options, option D is the correct solution of this question. Means statement 1, statement 2 and statement 3 are the correct. Solve this numerical. See, the field produced by the static charges is said to be an electrostatic electric field. So here we are going to say it is basically a conservative field. Means here the work you are going to done. Suppose if there is a small charge q, and if you want to move from position A to position B, see, the work is going to depend only on the initial position, the final position, and it is independent of the path you are going to travel. Then in that field is said to be a conservative field. Suppose in a conservative field, the work is going to depend only on the initial position, the final position, and it is independent of the path you are going to travel. Then that is said to be a conservative field. So therefore here there are two basic formulas regarding the potential difference between the 2 points and also the work done in order to carry a charge small q from position A to position B. So therefore VAB is equal to VB minus VA is equal to minus integral of A to B E bar dot DL bar, and work is equal to minus Q integral of A to B E bar dot DL bar. So you can see clearly this integral is going to depend only on the final position and the initial position, and here also same integral, it is going to depend upon only the final position and the initial position. So we can say the electric field is a conservative field because the potential difference and also the work done is going to depend only on the initial position and the final position, and it is independent of the path you are going to travel. Suppose if you are going to make a closed loop, suppose if I am going to make a closed loop in this path, then what is the net amount of work done and also what is the net amount of potential drop? So therefore we can say here this is a closed integral because we are going to make a closed path. So closed integral means the initial path is equal to final path. So therefore we can say this VAB will become 0 because both are identical. So therefore the difference is equal to 0 means the closed integral is equal to 0. So closed line integral of E bar dot DL bar is equal to 0. If this closed integral is equal to 0, here also closed integral, so therefore work is also equal to 0. So therefore we can say in a closed loop the net amount of potential drop is equal to 0, and also the net amount of work done in a closed loop is equal to 0 in a conservative field. See, by using the Stokes theorem, there is a relation between a closed and also the open surface, which is the closed integral of E bar dot DL bar is equal to open surface integral of del cross E bar dot DS bar. See, always a closed line can only enclose a open surface. So therefore we can say this is called the Stokes theorem. As the LHS is equal to 0, so definitely RHS is also equal to 0. So therefore we can say del cross E bar is equal to 0. It indicates that there is no curling, there is no curling effort is going to present in the electric field, means there is not even any curling effect, means we can say it is a irrotational, or we can say it is a electric field is always diverging but not having any curling effect. So therefore we can say curl of electric field is equal to 0. Yes, this is for electrostatic electric field, always curl of electric field is equal to 0, and this is the statement 1. Yes, statement 1 is a correct. And also see, this is also, suppose by Faraday's law we already know, which is del cross E bar is equal to minus dou P by dou T. It indicates that whenever there is a change of magnetic field, then we are going to produce the electric field, and the converse is also true. Whenever there is a change in electric field, magnetic field is also going to get produced. So therefore this is with the help of Faraday's law. Suppose in a static field means we are going to the magnetic field is a constant with respect to time. In a static field means whenever the magnetic field is constant with respect to time, then this partial differentiation will become 0. So therefore we can say del cross E bar is equal to 0. So in a static fields always del cross E bar is equal to 0, and the proof of E bar is equal to minus del V. This one I have just now in the previous example only I have told you. This electric field is always going to travel from the higher potential to lower potential, and it is a negative of the gradient of the scalar potential. So therefore statement 2 is also correct. So and also the statement 3 is the electric field is a conservative field because the potential drop and the potential difference and the work is going to depend only on the initial position, the final position, but not on the path travel. So therefore we can say basically the field produced by the electric charges. So we can say the field produced by the static charges is always conservative field, and also curl of the electric field is equal to 0, and we can say electric field is equal to minus of the gradient of the scalar potential V, and it's a conservative in nature. So these are the three statements are definitely true. For a static charges, field produced is called as the electric field. So now we are going to solve the 25th question. See the question here. Which one of the following is the correct statement? So equipotential lines and the field lines. So equipotential lines and the field lines are out of these four options, option C, they are orthogonal to each other. Means the electric field and the equipotential surfaces are always orthogonal to each other. So now we'll discuss the solution. So in this question they are asking what is the nature of the equipotential planes and also the electric field. So basically the potential difference between any 2 points, which is VAB is equal to VB minus VA is equal to minus of integral of A to B E bar dot DL bar. Suppose equipotential planes means the voltage at each and every point on that plane is same. Suppose I am going to take an equipotential plane with this is the point A and this is the point B. So therefore we can say VA is equal to VB. So VA is equal to VB because I am going to take these two as the same potential. So therefore if the
plane is called as the equipotential plane, means all the voltages at each and every point on that plane is same. So therefore VA is equal to VB. So if you substitute here VAB is equal to VB, so this value will become 0 because the difference will become 0. So 0 is equal to minus integral of A to B E bar dot DL bar. So we can say directly if this is 0, so we can say E bar dot DL bar is equal to 0. So E bar dot DL bar is nothing but E into DL into cos theta is equal to 0. So E and DL cannot be 0. So therefore definitely cos theta should be equal to 0. So whenever the cos theta is equal to 0,
it indicates that theta is equal to 90 degrees. So therefore theta is the angle between the E bar and DL bar. So therefore now suppose this is the electric field. So this is the electric field, then this is the 90 degrees. So therefore you have to move in the orthogonal, in the perpendicular to this electric field, then we can say this is called as the equipotential plane. So theta is equal to 90. The angle between the electric field and also the equipotential plane is 90 degree. Means these 2 points are orthogonal to this electric field. So therefore we can say the angle between the electric field and also the equipotential surface is 90 degree. Then only we can say that equipotential surface has each and every point same voltage. So therefore for a point charge, suppose there is a point charge, then the electric field will be radiating outward. It will be radiating outward. So therefore you have to move perpendicular to the electric field. Means I have to move perpendicular to the electric field. Means this is called as the spheres. So these are the spheres. So the point charge, the equipotential surfaces are in the shape of the spherical spheres. For a sheet charge, suppose there is a sheet charge. So sheet charge is going to, suppose it's a positive sheet charge, it is going to radiate the electric field in the upper plate upward and the down part is in this direction. So now I have to move orthogonal to this electric field. So therefore I have to move in this direction. So therefore we can say this is a plane which is orthogonal to the electric field. So therefore we can say this is called as the equipotential plane. So therefore we can say, see, a planes parallel to the sheet charge are called as the equipotential planes. These are the plane shape for a sheet charge. Suppose if you are going to take a line charge, so line charge is going to radiate the electric field. It is going to radiate the electric field. So now I have to move in the perpendicular to this electric field, then only I am going to get a equipotential plane. So therefore if you draw all these things, we are going to get a concentric cylinders. So therefore we can say for a point charge the equipotential planes are in the shape of a spherical spheres, and for a sheet charge the equipotential surfaces are in the shape of a sheet planes, the planes which are parallel to the surface sheet, and for line charge the equipotential surfaces are in the shape of a cylinders, concentric cylinders. So we can say these are the equipotential surfaces. So therefore the angle between the electric field and always the equipotential plane is always perpendicular to each other. So now we are going to solve the 26th question. See the question here. The capacitance of an insulated conducting sphere of radius r in vacuum is. So here there is a sphere of radius r. So in a vacuum, what is the capacitance which is offered by this sphere? We need to figure out the expression. So out of these four options, option B is the correct solution of this question, which is 4 pi epsilon naught r is the correct solution of this question. So let's solve this numerical. Suppose there is a sphere of radius r and it is going to have a small amount of charge q. It is going to present in a vacuum. So therefore we can say the relative permittivity of a vacuum is equal to 1. So now how much amount of capacitance offered by this sphere we need to figure out. So So if you are going to place this much amount of charge, then it is going to have some amount of voltage. The expression of the voltage is equal to charge by 4 pi epsilon naught r. So therefore this is the voltage of this much amount of voltage offered by these capacitors if you are going to keep this much amount of charge. So therefore now we can say here we are going to keep in a free space, or we can say vacuum, which is the relative permittivity of a vacuum or free space is 1. So therefore now here we can say the expression of the capacitance is equal to charge by voltage, and if you rearrange this one we are going to get 4 pi epsilon naught r. So therefore the capacitance offered by this sphere is equal to 4 pi epsilon naught r. So therefore we can say this much amount of capacitance offered, so therefore this much amount of charge, so this much amount of capacity is offered by this sphere in order to store a charge. So therefore this is the correct solution of this question. So now we are going to solve the 27th question. See the question here. Point charges of Q1 is equal to 2 nanocoulombs and Q2 is equal to 3 nanocoulombs are located at a distance apart. So with regards to the situation, which one of the following statements is not correct? So here in this question they are given two charges of 2 nanocoulomb and also 3 nanocoulomb. So now out of these four options, which option is the wrong option we need to figure out. So out of this, option B is the wrong statement, which is a charge of minus 5 nanocoulomb placed midway between the Q1 and Q2 will experience no force. So now we are going to solve this one. Option B is not a correct solution. So let us discuss the solution of the option B. See here, there are two charges, the charge Q1 of 2 nanocoulomb and charge Q2 of 3 nanocoulomb, and the distance between the charges is D. So therefore we can say here they are given option A, C, D. We are going to discuss the option A, C, D, and then we are going to see the option B. So therefore here these two charges are of same nature, positive charges. So therefore we can say like charges are going to get repelled. So therefore this charge is going to implement a force on this charge in this direction because it's a repulsive force, and here because of this charge it is going to make a force on this charge in the repulsive. So therefore we can say the magnitude of the force on individual charges is same but of opposite direction. So what is the magnitude of the force, which is Q1 into Q2 by 4 pi epsilon r square. So it is going to depend on the medium, and also because these two charges are same, the force is a repulsive. So therefore the force on 3 nanocoulomb is repulsive. Yes, it is going to repulse. Yes, option A is the correct. So force on Q1 and Q2 are same in magnitude. Yes, they are same in magnitude, but only thing is they are opposite to direction. So therefore this is also right solution. And here force is going to depends on medium. Yes, the force is also going to depends upon medium, which is the epsilon. Epsilon is going to tell you the medium in which these charges are going to get present. See, as the epsilon value increases, we can say the force is going to get decreased. So therefore except air, always the relative permittivity of any medium will be always greater than or equal to 1. Only for air or vacuum it is 1, and remaining any other medium it is always greater than 1. So therefore we can say as the epsilon value increases, the force is going to decrease. Means we can say blindly the force between the two charges is very much high only in the free space or vacuum, but not in any other medium. So in any other medium the force value will goes on decreases because the relative permittivity value is always greater than 1. So the definition of permittivity means here it is an opposition to an electric field in a given medium. If the permittivity means it is going to oppose the electric field in a medium, that is the meaning of the permittivity. It is going to basically oppose the electric field in a medium. So option A, option C and option D are right. So we have to find what is the incorrect statement we need to figure out in this solution, in this question. So therefore here in the option B they have told that here the charge Q1 is equal to 2 nanocoulomb and charge Q2 is equal to 3 nanocoulomb, and there is another charge Q3 which is minus 5 nanocoulomb which is present midway between the charges. Means if the distance between the charges is D, it is going to present in midway, means equal distance, which is D by 2 and D by 2. So now I want to know what is the force on this charge. I need to figure out whether this charge is going to remain stationary or it is going to experience a net force. We need to figure out. See here is a positive charge and negative charge. So therefore unlike charges they are going to get attract. So this is the attraction. So because of this charge is going to face an attraction, which is, let me assume this is F1. Similarly these are also opposite charges, so then also it is going to experience an attractive force. So therefore Q2 will make a force on this Q3 in this direction of opposite, means attraction. So therefore this is F1 and F2. If F1 is equal to F2, then we can say this charge will be stationary. If suppose F1 is greater than F2, means this charge is going to move in this direction. If F2 is greater than F1, means this charge is going to move in this direction, means it is not in a rest condition. So now we have to see what is the nature of the F1 and F2. See, F1 is equal to, only we have to find what is the magnitude. So therefore product of the charges by 4 pi epsilon into distance whole square. So 2 into 10 to the power of minus 9 into 5 into 10 to the power of minus 9 by 4 pi epsilon into d by 2 whole square. So if you do the product, we are going to get 10 into 10 to the power of minus 18 by 4 pi epsilon d by 2 whole square. So now I want to know what is the force between these two charges. So it's attractive force. So F2 is equal to product of the charges by 4 pi epsilon distance whole square. So therefore 3 into 10 to the power of minus 9 into 5 into 10 to the power of minus 9 by 4 pi epsilon d by 2 whole square. So if you do the product, we are going to get 15 into 10 to the power of minus 18 by 4 pi epsilon d by 2 whole square. So you can see clearly the numerator of the F2 is greater than the numerator of the F1. So therefore we can say F2 value is higher than the F1 value. So if F2 is higher than F1, it indicates that this charge is going to move in the direction of the charge Q2, because here the net force is very higher when compared to the net force F1. So therefore we can say this charge is not at all at rest, because one force is higher than the other force. So therefore we can say F2 is not equal to F1, or we can say F2 is greater than F1. So therefore we can say simply this charge is not at all at rest. It is going to experience a net force and it is going to move in the direction of the net force. This charge is going to face the net force in the direction of F2. So therefore this charge is going to move in the direction of the charge Q2. So option B, in the option B they have told that this is going to remain at rest, but practically no, it is not going to remain at rest. So therefore we can say option B is the incorrect statement. In the question they are asked which is the wrong statement. So therefore option B is the correct solution of this question. Now we are going to solve the 28th question. See the question here. Assertion: the electric field around a positive charge is outward, and the reason are the Gauss law states that the differential of the normal component of the outward electric flux density over a closed surface yields the positive charge enclosed. So out of this assertion and reason, assertion is correct but the reason is wrong. So now we'll discuss the solution. Always the positive charge is going to radiate the electric field outward, whereas the negative charge, it is going to invert the electric field towards its charge. So as per the Gauss law is going to tell you the amount of total flux which is coming out of a closed surface is equal to the amount of charge enclosed by that Gaussian closed surface. So therefore we can see here, we can write in another manner, which is the surface integral of the closed surface integral of the d bar dot ds bar is equal to volume integral of the rho v dv. So we say this as a integral form of a Gauss law. So we can write the closed surface with the volume relation by using the Gauss divergence theorem. So we can write a closed surface with a volume, because only a closed surface can only give you a volume. So therefore we can say closed surface integral of d bar dot ds bar is equal to volume integral of the del dot d bar into dv. This we are going to say it as a Gauss divergence theorem. So by seeing these above two equations, the LHS are same, so therefore we are going to equate the RHS. So therefore we can say del dot d bar is equal to rho v. It indicates that the divergence of the electric flux density is equal to volume charge density. We are going to say it as the differential form of the Gauss law. So therefore the Gauss law is going to always tell you the amount of flux coming out of a closed surface is equal to the amount of charge enclosed by that closed surface. Always for a positive charge, it is going to radiate the electric field, whereas the negative charge, it is going to take the inward, or you can say the electric field is directed towards the charge. So therefore you can say assertion is correct but the reason is wrong. So the reason is nothing but here, the reason should be in this manner, which is the amount of electric flux passing through a closed surface is equal to the amount of charge enclosed by that surface. This is called as the Gauss theorem. So now we are going to solve the 29th question. See the question here. The electric field strength at any point at distance of r from the point charge q located in a homogeneous isotropic medium with the dielectric constant epsilon r is given by. So here there is a charge q. We have to find what is the magnitude of the electric field at any point which is a distance of r from the charge. So the medium is a homogeneous isotropic medium. So now here we have to find what is the expression of the electric field. So out of these four options, option A is the correct solution of this question. So let's solve this numerical. So before I solve this numerical, let me tell you a small concept. There are two types of mediums which are going to present, which are the isotropic medium and the another thing is the anisotropic medium. So isotropic medium means the permittivity of the medium at each and every point in a space is constant. Then we are going to say it as the isotropic medium. Suppose or we can even say the material properties are same at each and every point in the space, then we are going to say it as the isotropic medium. Otherwise, if the relative permittivity is not constant constant at each and every point in space, or if the material properties are going to change with respect to the point in space, then we are going to say it as the anisotropic medium. But in the question they are given only isotropic medium, means at each and every point in the space the relative permittivity is a constant value. So therefore now suppose there is a charge q at a point P. This point is at the distance of r from the charge. We have to find what is the electric field at that point. We need to figure out. So the expression of the electric field is nothing but q by 4 pi epsilon r square in the direction of r cap. So now here I can write this expression in the another format, which is E bar is equal to q into epsilon inverse by 4 pi r square into r cap. See, this is the correct solution of this question. See, I can write in another format also, which is r cap is equal to r bar by magnitude of that vector. So magnitude of that vector I can write is equal to r. So therefore r bar by r. I can replace r cap by r bar by r in this expression. So if we do the simplification, finally we are going to get E bar is equal to q by 4 pi epsilon r cube into r bar. So you can go for either this one or this one. So in the options only this option is present. So therefore we can say this is the correct solution of this question. So we are going to solve the last question of this lesson. See the question here. Two charges are placed at distance apart. Now if a glass slab is inserted between them, then the force between the charges will. So here first thing is they have kept in a medium. So now we are going to keep a glass slab. Then what is the force between these charges we have to know. So whether it will increase or decrease or remains constant. So out of these four options, option C, it is going to get decrease. So now we'll discuss the solution. So here suppose let me take a medium one. So the medium one is a vacuum. So now here I am going to keep a two charges. See at distance of r. Then what is the force between these two charges, which is q1 to q2 by 4 by epsilon r square, where epsilon is called as the permittivity of a medium. So basically permittivity means it is an opposition to an electric field in a given space or region. It is called as a permittivity. As the permittivity increases, we can say the force value will decrease. So therefore permittivity is equal to epsilon naught into epsilon r. So for a vacuum, or we can say for air, the epsilon r value is equal to 1. So therefore if you substitute here, we are going to get F1 is equal to q1 q2 by 4 pi epsilon naught r square. This is the equation 1. Suppose these two charges, between these two charges I am going to keep a medium. That medium is called as a glass. So suppose I am going to keep a glass. So glass is going to have some dielectric constant, or we can say dielectric constant is also called as the relative permittivity. So therefore for always a glass, the epsilon r value will be always greater than 1. So therefore we can say for a glass always the relative permittivity or the dielectric constant is always greater than 1. So now what is the amount of force? So let me assume the force is equal to F2, which is q1 q2 by 4 pi epsilon r square. Now epsilon is equal to epsilon naught into epsilon r. Here epsilon r is not equal to 1 because it is a slab, it is greater than 1. So therefore we can say substitute this one here, we are going to get F2 is equal to q1 q2 by 4 pi epsilon naught into epsilon r into r square. This is the equation 2. So now I am dividing the equation 1 by equation 2. We are going to get F1 by F2 is equal to epsilon r. So therefore F2 is equal to F1 by epsilon r. As epsilon r is always greater than 1, so therefore we can say F2 value will be lesser than F1. So therefore the force between the charges in the medium, in the glass medium, is very less when compared to force between the charges in a vacuum or free space. So always the range of the relative permittivity is always greater than or equal to 1. This is the range of the relative permittivity, which is always greater than or equal to 1, and its value is 1 for the vacuum or free space or air, and it is equal to 81 for the water. So these are the two general cases. So if you take any other medium except vacuum or air, the epsilon r value will be always greater than 1. So therefore we can say as epsilon r value increases, we can say the force will decrease. So this is the reason if you keep a glass between the charges, we can say the force value will decreases because the relative permittivity or the dielectric value constant is increases. So therefore they are inversely proportional. So force is going to get decrease. So decrease is the correct solution of this question. So by this lecture we have successfully completed the 30 questions of the electromagnetic theory of ESE examinations of previous year questions in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, the direct notification comes to mobile. If any improvements needed in our video lectures, then please do comment in the comment section. So we'll definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care, and bye bye.